Oh. Good work, Maddie. Thank you.
So we start with this one, right?
Doesn't that go?
We're missing
Do whichever one you want. Yeah, actually, do the extra credit one first.
Okay. Is there like a question prompt?
Okay, the extra credit one I can just tell you. The extra credit one says that the centrifuge is at an angle of 15 degrees from the horizontal. What's the centripetal acceleration?
Okay. So, can we move the screen? Is that like
just
two
scroll with your
fingers?
finger.
Okay.
You can only scroll that way, or you can scroll
Okay.
left, right.
So let's say we had the thing. This is like the device that's making everything happen. And then at some point, there's an angle branching off. That's 15, right?
Yeah, that's correct.
And then you have the box that the person's spinning in. And this would make like a 90-degree angle. And then we're asked to find centripetal acceleration, right? Okay. I need a refresher on what equation I used.
You can look at what you sent me.
Okay. So if we break this up into components, X and Oklahoma Raiders,
It's that one.
and Y, we see that acceleration in the Y direction is 0 because it's not going up or down or anything. It's just going in that circle, not any angles. And we don't know the acceleration over here. That's why we're trying to solve for it. But we do know that the acceleration going on in the X direction is caused by the tension going on over here. And so the force of tension is in effect, but it's not all being directed into the box because it's split by that 15-degree angle. So it's actually the cosine of this. And then over here in the Y, we got the force of gravity pushing it down, which we're defining as negative for common reasons. And then once again, the force of tension, but this time in the sine direction. And so we know that the sum of the forces is equal to just the only force in the X direction. Whereas the sum of the forces in the Y direction is equal to the force of the tension minus that of gravity. And we know that all of that is equal to 0. Oh, we also know that force is always equal to ma. Separation. Cool. So now we don't know what t is, but since we have t in two different dimensions and the t is equal, we're acting upon both, we can solve for it and then put it into the x direction to find what we want, because we're looking for this. And so, change the colors again. T on this side will be equal to moving the mass and the gravity over and then dividing that by the angle. And then if we bring that over to the x side, we have T, aka mass gravity. This might be too close, but we'll see. 15 times the cosine of 15 equals ma. And then both of our masses, whoa, what's going on? Cancel out. If we divide by mass. So we have A equals G, which we know to be 9.8, times cosine over sine, 15. Which, if I had a calculator, I could, like, oh, how convenient. You ask for things in life and they come to you.
I mean, like the lottery. It's winning the lottery ticket, not just the lottery ticket.
And plugging that in now, I got 36.574, etc., which seems familiar, which is good. So we use sig figs, we were given 15. So we would say that the acceleration is equal to about 37 meters per second squared. And that's the other problem.
Now, any questions about that? That was, of course, what we were practicing in lab, so going up and do the other one, which is using universal gravitation.
Okay. So this one should use one of our fancy gravity laws, which I look up because obviously
G times M1 times M2 over R squared.
Let's do dark one. G equals big G.
Oh, okay. If we're doing little g, G is going to be then just the mass of the moon over the radius of the moon squared. Well, no, it's still the capital G, I'm sorry. You haven't written anything that was incorrect yet. It's just I gave you the equation for force. So it's lowercase g is capital G times mass of the moon divided by radius of the moon squared.
Yeah, which I thought was the one you were going for, unless you're going for the other one.
I had put the other M on it to make it force. That was the only difference. Force of gravity is G M1 M2 over R squared.
Yeah.
G is capital G M1 over R squared.
Okay. M1.
Okay, that didn't translate quite right. It should be erase your equal sign.
Oh,
This
flip
one.
it over.
And then it should be lowercase g is equal to capital G times M1 over R. Right.
Oh, okay, I see. Same thing, just solving with the. Okay. Yeah, so that's what we use. Because we know that we're given the force gravity. And we're giving M1 to be 7.35 times 10 to the 22. G is the constant, which we are reminded of. And we're given R to be 1.74 times 10 to the 6, which we'll just use that as our weird notation for that. Okay. So given all that, we should, I think, so we're trying to calculate the mass of the astronaut in kilograms. See, I feel like that'd be the other one with the M1 and M2.
Well, the force equation is capital G M1 M2 over R squared.
Okay, yeah. Oops. So then if we solve it all.
G, then not G equals, but F sub G. Right, that was why I stopped you at the beginning, because you put lowercase g equals. There we go.
Oh, okay. There we go. Everything's coming together now. And then there's the thing that keeps happening. I keep doing that. Oh, I'm hitting the home button. There we go. Okay, so if we want to solve for mass 2, we'll say, because we've made mass 1 the moon, we'll basically do the reciprocal. So it's Fg times r squared divided by big G m1. Which, could you calculate that? Which is what, r 100 newtons
And then
times G f of G, which would be, that's already there, times r squared. So 1.74 times 10 to the 6 in normal notation this time. And then the gravitational constant, 6.67 times 10 to the negative 11 times the mass of the moon, which is 7.35 times 10 to the 22.
that seems
You have to square the radius.
so then. Okay.
Because right now it's not. Yeah.
What we got the first.
Oh, okay, that's fine. He's on a different planet.
Yeah. 67.9.
It's just calculator work.
Yeah.
Right, all the work is correct, so I'm happy with that. All right, so that,
Yeah.
how much would this guy weigh roughly on Earth? Acceleration of gravity is 9.8 meters per second squared, right? So that's roughly 10. So he'd weigh roughly 600, well, let's say 670 newtons on Earth, and it's only 110 newtons on the moon. So his weight is very different on the moon compared to on the Earth. But his mass is going to be the same. His mass is a measurement of how much stuff you're made of, and the weight is the force the gravity puts on that. All right, thank you. From Jeff. All right. Uh-oh. I thought I had started the presentation. It might not work writing. That's at least my theory. So I'm going to talk about work and energy. The first few problems for the homework that's due tonight are work and energy because that's supposed to cover 7.1 on Wednesday. So energy is really important to our lives. Understanding about energy is really important. Energy is another way of solving the problems we just finished solving. We've just finished solving problems using Newton's second law as our fundamental way of solving problems. And it works very well, but energy is easier. And some of you are probably already starting to steam inside saying, why did you teach us the hard way first? Why didn't we do the easy way first? And the reason is you have to understand forces, how they work, before you can do the energy method. So you have to have that ability before you can go on to the energy way to solve the problems. So what is energy? Energy is the ability to do work. So we have to define work before we can go anywhere with energy. So work is force that is accompanied with motion parallel to the force. So here we have a math symbol you may or may not be familiar with. Depends on your math background. It's a part of vector algebra. This dot here, good, it's writing, means that you're multiplying parallel parts of vectors. Parallel parts of vectors. So notice there's a vector sign over the F and a vector sign over the X. And work is force dot distance travel. Force times distance travel parallel. So I always do the simple example like the picture shows, the man with the briefcase. Here's my briefcase. So I have this right now. Am I doing any work on it? Why do you say no? What?
The force is acting on me.
Well, Newton's third law says if there's a force acting on me from it, then I am putting a force on it. So I am putting a force on it. I'm putting an upward force. That was actually one of my follow-up questions. Am I putting a force on it? Absolutely, I'm putting a force. I'm putting a force upward on it.
There's no directions.
But there is no motion. No motion, hence no work, because you have to have force and motion. So then if I walk at a constant speed, let's pretend it's perfectly constant speed, am I doing any work on it?
It's still not moving.
Well, it's moving in this direction,
But it's not parallel to the.
but it's not parallel to the force. So there's still no work being done if I'm moving with a constant velocity that's perpendicular to the force. Now if I go like this, is there work being done on it?
Yes.
Yes, if I raise it, then the force I'm applying is up, the direction it moves is up. If they're in the same direction, that's going to be a positive work. If I come down, am I putting a force on as I come down? Yes, it's not falling. It's not falling with any acceleration. So I have an upward force that's equal to the force of gravity. My velocity is constant. But my force is up and the velocity is down, or the delta x is down. So in that case, I'm doing a negative work on it. Gravity was doing a positive work on it when it came down. Gravity was doing a negative work when it went up. So the key here is you have to have motion parallel to the force to do positive work, or motion anti-parallel to the force to do negative work. So in this picture, we have a guy pushing the lawnmower, and let's be honest, you don't push straight down that handle, right? You'd be driving the lawnmower a lot into the lawn. But this picture is simplified, saying that he's pushing straight down the handle. Is he doing any work on the lawnmower as it moves at a constant velocity through the yard? Nathan says yes. Why are you saying yes, Nathan? Because a component of his force, the force he's applying times cosine of the angle, is parallel to the motion. So some of his force is doing work. Some of the force is not, but some is. And so is there work? Yes. So now let's look at these. Is there any work being done by the man on the briefcase there? Notice it's only showing the force the man's applying to the briefcase. Is he doing any work on the briefcase there? Okay, I've got people shaking their heads. Both of them shook their head no. Andrew, why'd you say no? Because there's no moment, right? It says D equals 0 there, and you have to have a change in position. Okay, what about C here? Is there any work being done by the man on the briefcase there? Now I only have one person shaking their head.
No.
Okay, no. Thank you, Ryan. Why'd you say no, Ryan?
It's not parallel to the.
Right. There's motion, but the motion is perpendicular to the force the man is applying. In this case here, we have the force of the man as he's going up the stairs. Is he doing work on the briefcase as he's going up the stairs? Yes. Why? There's a component of his force that's parallel to the motion. And finally, the man, for some reason only God knows, ties his briefcase to a winch and has the winch lowering his briefcase. Is the winch doing any work on his briefcase? Yes. What makes you say, I think so, instead of being 100% positive?
Because there's force.
They don't have to be in the same direction to be parallel to each other.
Well, in this case, we call this anti-parallel. One's up, one's down, and that's going to result in the winch doing a negative work on it. Instead of a positive work, it's doing negative work. So I would still say, yes, that's work, but you have to understand the work is a negative value here. So in calculating the work, remember it was force dotted to change in position is work. And so if you make a graph and you put force on the vertical axis and position on the horizontal axis, then force times change in position, if you had a constant force, it would just be the height times the width of the box as shown there. And what would we call the height times the width of a box? The area, which it probably says somewhere over here on the right. So work can also be calculated from a graph by taking the area under the curve of a force versus position graph. For those of you who are not in the calculus-based class, that's the only way you're going to be able to calculate the work if you have a non-constant force, is by looking at the graph and calculating the area. Now, those in calculus know that we can find this area under the curve by integrating. That's what the integral means. So you're going to need to be able to do that to calculate work from the area under a curve. Well, let's go back. Let's take the example of the force of a spring. Force of the spring is Kx. So if I make a graph of force it's a straight line like this, with the equation for this line is force equals Kx. So if I want to find the area required to stretch the spring by some distance, that was not the color I wanted to choose. That was the one I went for. Some distance x0. If I want to find the area there, what's my shape? It's a geometric shape that you should know the area. So what's the name for that shape? The shape that's under the curve. A triangle. What's the equation for the area of a triangle? So work is equal to the area is equal to 1/2 the base times the height. Oops. That was the next to last slide there that we got to. I went through like 3. 1/2 base times height. If we start at 0, 0, what's the base? We have x0 minus 0. What's the height? The height is kx sub 0. And if you want to be technical like we were before, minus 0. So that's 1/2 k x0 squared. So the work done by stretching a spring is 1/2 the spring constant times the amount you stretch it squared. So that's one way of using this new method to find work. Now, our first practical example, we have this mass, 30 kilogram mass. It's on a conveyor, well, not a conveyor belt. It's on one of those little roller things. I see she's still in a wheelchair.
Oh, no, she can walk. It's just as she feels.
Okay, she just said it. Okay, so in this situation, there are two forces. The force applied, well, there's four forces. Force applied, a force of friction that's shown with the lowercase f, a force of gravity shown as W, and a force normal. Let's calculate the work for each one of these. Work applied. What's the work applied?
Would be the 120 minus 5 times 0.8.
Actually, you did the net work. I'm looking at only the work applied. So that's just going to be the force applied dotted to my delta x. And Nathan went ahead and gave me a number already. So my force applied is 120 newtons. The distance it moves is I need the distance parallel. What's the distance parallel to the force applied? 0.800 meters. And so 0.8 times 120 is 96. And what are my units going to be? Newton times meter. We have another name for that unit. Newton times meter is a derived unit, right? That's equal to kilogram meter per second squared times meter, or kilogram meter squared per second squared. We also call a joule, J for joule. Joule is spelled Joule. It's a dude's last name. We pronounce it his way. I had a teacher that was, I think he just thought he was really funny because, we physicists tend to think we're funny. He said we should call these joules. And he, used some example of O-U-L-E that sounded like owl. But it's a dude's last name, Joule. So 96 joules is supplied by the force applied. Okay, how about the work by friction? What's that going to be?
It'd be the negative 5 times 0.8.
Okay, I'm going to put the numbers in different way than you did, but you said it perfectly. So I put the negative sign with the distance because the distance is opposite to the force, and I treat the force as the positive one. Okay, so you're going to get the same answer either way. So what you said was perfectly correct. The minus sign there is because the force and the distance are in opposite directions. 5 times A is 40, so equals minus 4.0 joules. Okay, what about the work done by gravity?
It's perpendicular to that, so it doesn't have any angle.
Does that make sense to you guys? Because the distance is perpendicular to the force of gravity, the work done by gravity is 0. And what about the work done by the force normal? Same. So those are zeros because the force is perpendicular. We are just throwing in a whole bunch of concepts so we can get to a problem in 5 minutes. Potential energy. So we've calculated work. Work is the result of a force acting on an object making it move. To make life, just to make a connection, let's say that you are trying to hold up the sofa while your friend is vacuuming underneath, or your roommate, because you clean your room, right? You vacuum under the sofa, like you have sofas in your rooms, right? So you're sitting there holding it, and if your friend is in the middle of doing this, checking their email and stuff, and you're there for 5 minutes, you're gonna start to get tired, right? According to physics, you're just sitting here holding it. Are you doing any work? No. According to life, are you doing any work? Yeah. What's the difference? What we're talking about here is technically the mechanical work. So when I'm saying work here, I'm meaning mechanical work. And the mechanical work is the work that has to do with motion. You do have biological work that you're doing when you're holding that. That is, your body is converting energy to keep your muscles holding that thing. And so there is biological work involved, just not in mechanical work when you're sitting there holding stationary on the sofa. On the other hand, as Sarah sits in her chair, is her chair doing any work on her? No, it's not doing any biological work, and it's certainly doing no mechanical work. And so she can sit there on the chair all day long. There's no energy conversions going on, no work. So I just used energy, probably not for the first time, but for the first meaningful time. Energy is the ability to do work. If something has energy, it can do work. If it has no energy, it can't do work. So potential energy is defined as the ability to do work because of position or configuration. So a lot of you have already taken a chemistry class, and you've learned about bond energies and things like that. Well, you have potential energy because of the force between the bonds. You have an electrostatic force that is, well, it's pretty complicated when you get down to the quantum mechanics of it, but it's an electrostatic force that is holding two molecules together, or I said static. I should just say electromagnetic and not, it's not static. You have an electromagnetic force that's holding two molecules together, or holding an electron to a nucleus. And there is potential energy because of the configuration, because of the positions and separations. We're going to start with the easiest one, and that's gravity. It's pretty clear that if I hold this ball up here, if I let go, gravity is going to do work on it. There's going to be a downward force, and it's going to move parallel to that. So gravity did work on it. So gravity had the ability to do work based on its position. If I put it here, can gravity do the same amount of work, more work, or less work? Less, because it has less distance that it can fall with that force of gravity pushing on it. So the gravitational potential energy is going to have to do with only the direction that is parallel to the force of gravity. By definition, gravity is acting downward. So it's only going to have to do with vertical position. And it's going to be the force of gravity. Remember, force times distance. Force of gravity times the height. So gravitational potential energy, force of gravity, mg, multiplied by the elevation. Here's an important thing to help you. Height, where should you measure height from?
The surface that should hit.
Okay, the surface is going to hit. Is that what you said as well? I thought. The what?
The center of the object.
Okay, center of the object to Earth. If you're talking about something that's near the surface of the Earth, where g is a constant, then you can choose your reference point wherever you jolly well please. You can choose the reference point to be the starting position, the ending position, or any other place you like. Your problem will still work out correctly. Now, if you're using something that's moving significantly away from the surface of the Earth, where you have to use force of gravity as gm1m2 over r squared, then we use as our reference point that you have zero potential energy when it's infinitely far away, and the potential energy is going negative as it's closer. You have to use a different equation in that case as well. The equation for potential energy due to gravity, which comes through calculus, in the case of not being near the surface of the Earth, potential energy gravity is equal to minus mass 1 mass 2, forgot the G, over R. Now here's the crazy thing. How is that different from the force of gravity? Okay, it doesn't have radius squared. The force of gravity is a vector. This is a scalar. It doesn't have a direction to it. That's why the energy method is easier, because energy is a scalar. That dot product multiplying the parallel parts is also called a scalar product because it gives you a scalar result with no direction. And so this here is just like the force of gravity, but has a minus sign. Force of gravity, it's a vector, so, and it's divided by r instead of r squared. And somebody might naively think, well, that's the force of gravity, gm1 m2 over r squared, times the distance, r. But that would be incorrect. Because the distance it moves is not the same as the distance that's separating two objects. They're two different things. And it actually comes from doing an integral to get this. So that's how you get the equation. We're not going through how to get the equation in this class. Next Tuesday? Sure. So that's how potential energy works. This little example is showing the old cuckoo clock or whatever that uses weights to run. When I was a kid, my grandparents, well, my grandmother, my grandfather was dead, had one of these. And I was just kind of like, how in the world does that work? They come and they pull the weight up, and then the clock runs and keeps running, but the weights go down, and then they come and pull it up again. Well, they're using the weights in the same fashion that we use a battery. A battery is storing energy in the form of a chemical reaction. This system here is storing energy in the form of gravitational potential energy. Has the ability to do work because of that gravitational potential energy. And as it falls, it's converting energy from the potential energy into making the clock run. Okay, this is our next to last slide. The next one is the problem. Here's a fun example, and one that you cannot do without hard calculus and knowing the exact shape of the track using forces. We have a roller coaster, and you start at the top, and you go down 25 meters from there, and then you come up to 20, and we ask, what's the speed at the finish line, assuming no friction? If there's friction, the friction is going to be acting in the direction opposite to the motion. So is that going to do a positive or negative work, or zero work? It's going to do a negative work because the force is opposite to the direction it moves. So the friction is going to reduce energy. But if we have no friction, then we have nothing to reduce energy. Now there's another equation here, kinetic energy. Kinetic energy, the ability to do work because of motion. And that one's really easy to understand. If I come running at you, and then I hit you, will I do work on you? Will I apply force, and will you move? Yes, if I run and hit you, I will apply a force, and you will move. So I will do work on you. In that case, it's not because of my position, it's because I was moving. Moving kinematics. So kinetic energy is energy because something is moving. And the equation for that, which once again we get through calculus, is 1/2 mass times the speed squared. So you double the speed, you have 4 times the kinetic energy. And then there's this thing we call the work energy principle that says the network is changing kinetic energy. Now I'm going to go one step further before I solve this. We said that potential energy, I didn't say this part and I should have. Conservative work, that's work done by forces that will give you back the energy. What's a conservative force? As far as you're concerned, friction is not conservative. Work done by a machine or a person is not conservative. The work done by other things like force of gravity, force of a spring, that's conservative. The work conservative is defined as minus the change in potential energy, or actually change in potential energy is defined as minus the work conservative. And so since change in potential energy is equal to minus work conservative, then work net can be broken up into work non-conservative, that's work done by friction, work done by you or a machine, plus the work conservative, which would be work non-conservative minus change in potential energy. But the work energy principle says the net work is changing kinetic energy, so that means work non-conservative minus change in potential energy is changing kinetic energy. And so if I solve that for work non-conservative, I get work non-conservative is equal to change in kinetic energy plus change in potential energy. So when we work out work energy problems, I recommend starting with that equation. Work non-conservative is change in kinetic energy plus change in potential energy. Then we look at the problem, we say, okay, is there non-conservative work? In this case, that would be, is there friction acting on the cart? Yes or no? No. Is there a person pushing or pulling on the cart? No. Is there a machine pushing or pulling on the cart? No. Then work non-conservative is 0. That's as far as we're going to go for that analysis. So in this case, we say work non-conservative equals 0. And then we say, what's the kinetic energy at the start? 0, because it's 1/2 mass times 0 squared. What's the kinetic energy at the end? I don't know its value, right? But I know it's going to be 1/2 mass times speed final squared. So I write that down on my figure. I write down the initial kinetic energy and the final kinetic energy. I identified that work non-conservative was 0. Last step, same thing for potential energy. Now for potential energy, I need to define where will I use my reference point. Where would you like to use? Okay, I'm going to tell you where I want to use. I want to use the starting point as 0 potential energy. Why am I choosing the starting point? Because that would allow me to find the speed both at the lowest point and at the finish line in the simplest fashion. So I'm going to set Y initial is equal to 0. So potential energy initial equals 0. And potential energy final is going to be mass times gravity times minus 20 meters because its position is now 20 meters below the starting point. And then I just use this relationship right here. 0 is equal to, change is always final minus initial. So 1/2 mass times speed final squared minus 0. That's the change in kinetic energy. Plus the change in potential energy. The final is mg times minus 20 meters minus the initial of 0. And now I have an equation that I can solve pretty much instantly. Notice the mass cancels out. And I will have 1/2 b squared equals g times 20. Equals g times 20 because I moved it across. So multiply both sides by 2. 2g times 20, 40g. 40 times 9.8 is approximately 400. And square root of 400 is 20. So I get right away that the V final is 20 meters per second there. Now, there's only 4 minutes left. I want to make sure I worked a problem before I set you on your problem. If your problem has 3 pieces, there's no way you're going to finish it. You have a roller coaster, and it first asks, what's the speed of the roller coaster in meters per second at the top if you have this radius, and this is the downward acceleration at the top. What would you call the downward acceleration at the top? The centripetal acceleration. Because at the top, downward is toward the center. And so your centripetal acceleration is 1.6 g. I'm just going through and leading you through this because we don't have time to do it. I mean, there's no way anyone's going to get the full set of answers. So centripetal acceleration is 1.6 g's. that means you're being pushed down by the seat 60% more than you are when you're stationary. But we know that AC is V squared over R. So that allows you to calculate what the speed is. Then it asks, how high above the top of the roller coaster must you start, or the loop must you start to reach this speed? And so if you're going to reach that speed, then you use the problem that we just did. Okay, nice drawing. There's our roller coaster ride. So you start up here, and you're finding this distance necessary to have that speed. And so you would use exactly the same formalism that I did here. You want to calculate what's the kinetic energy and potential energy at the top, just like before. Potential energy initial, I'll say, is 0. Kinetic energy initial is 0. And here we have potential energy final is equal to minus mg. I put minus mgh because I defined this as h and it's going down. And kinetic energy final is 1/2 mv squared. But we had right here v squared is 1.6 rg. And so then I use my work energy relation. Work non-conservative, assuming no friction, that's 0, is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And so now I just solve this for H. Cancel what I can. And I have H is equal to R times 1.6 over 2. And so 7 times 1.6 is the height that I would need to be above the top of the loop when I start. Right? You never would have gotten through this problem in the time allotted. Okay, it's time for the weekend. Have a great one.